So today we're going to discuss the notion of a vector space or a linear space. So this is one of the most important notions in linear algebra, and it is introduced using an axiomatic definition. So in this sense, this definition goes along with other algebraic structures that we have already discussed, such as groups, rings or fields. And as it always happens with this kind of algebraic definitions, such algebraic structure inherits some properties of an existing object. So we have some modeling example that is being taken as a basis for this abstract algebraic definition. So in the case of a vector space, the coordinate space Rn serves as such an object. So we have already discussed the coordinate space Rn. So this is the space of n tuples of real numbers, and we can add these n tuples that are called vectors, and we can multiply these vectors by real numbers, and these vectors and algebraic operations with these vectors, they satisfy a number of natural algebraic properties. And some of these properties are included into this axiomatic definition of a linear space or a vector space, and they allow to formalize this concept that inherits some properties of the coordinate space Rn. And as we have already discussed, we can consider not only the coordinate space Rn, but the coordinate space Fn, where F is some field. And since all algebraic properties of the set of real numbers are also satisfied by elements of other fields. I mean, by saying algebraic properties, I mean that properties like commutativity and all that. Of course, not all properties of real numbers are satisfied for any other field, so there are topological properties and all that, so I do not discuss this now. But when we say about these algebraic properties, they are also satisfied for the field, for any field, and that's why we can consider the coordinate space Fn. And as we have already discussed, all the things that we discussed for real numbers, like Gaussian elimination and all that, and matrices with real entries. So this can be extended to the case of arbitrary field. And so we can also formulate the notions, we can also formulate standard results about the dimensions of the space of the dimension of the space of solutions and so on. So now we will give this definition of a vector space, but before I do this, so I'll write that this is the, so now we start the second part of this course, which is vector spaces. And so the first section would be vector spaces and subspaces. And subsection 1.1 is about the definition of a vector space. So the definition. Let F be a field. Then the set then the set V equipped with two mappings so the first of them will be denoted by plus, so it acts on the Cartesian product of this set by itself and it takes its values in V. So the set equipped with two mappings, so this is the first mapping and the second mapping is denoted by dot, so it is defined on the Cartesian product of the field by this set V. So F multiplied by V, and it takes its values in the set V. So this set equipped with these two mappings is called a vector space. Or a linear space over F if the following properties are satisfied. So the first property is commutativity, so U plus V equals V plus U for all U and V from this set. So we have already seen the property of this kind in the definition of a group. So the second property is the property of associativity, so this means that U plus V then plus W equals U plus V plus W for all U, V, and W from V. So this is the property of associativity. Then the third property is the existence of the additive identity. So there exists an element 0, I will denote it like 0, such that V plus 0 equals 0 plus V equals 0 for all V from V. So, of course, since this operation is commutative, there is no need in writing two of these properties, just because one of them follows from the other one. So the fourth property, for every V from V, there exists the element minus V from V capital, such that V plus minus V is 0. Okay, so we can observe that these four properties mean nothing but the fact that the set V forms an abelian group with respect to this operation. But this is not enough to define the structure of a vector space. We need more properties, and so the fifth property would be that lambda multiplied by U plus V equals lambda multiplied by U plus lambda multiplied by V for all U, V from V, and for every lambda from the field. So here we introduce the elements from the field. In the first part of the definition, we were working only with the elements of the set V. Then the sixth property is that lambda plus mu multiplied by v equals lambda multiplied by plus mu multiplied by v for all lambda mu from the field and for every v from v capital. And so two more properties, I'm going to fit them here. So lambda multiplied by mu multiplied by v equals lambda multiplied by mu and then multiplied by v. So for every lambda and mu from the field and for every v from v. And the last property states that if we take the multiplicative identity from the field and multiply it by a vector v, we get v for every v from v. So for every v lowercase from v capital. So these 8 properties should be satisfied, and once they are satisfied, we call this set a vector space or a linear space. So the properties number 5 and number 6 are called distributivity. So there are 2 different distributivities here, because in the first of them we add vectors, and in the second of them we add elements of the field. But both of them are called the distributivity property. Okay, then I need to make a few remarks here. First of all, let us look at the property number 6. If one wants to be more rigorous, so we can notice that here we have 2 different operations denoted by the same by the same notation. So here we add elements of the field. In the left-hand side of the property 6, we take the sum of the elements of the field. So lambda and mu are elements of the field, and in the field f we have 2 operations, and then the first of them is denoted also by plus, and so this is the plus from the field. So we add 2 elements of the field in the left-hand side. But in the right-hand side, here we consider this plus, the plus which acts on the Cartesian product of v by itself. And so here we add vectors. So to be fully rigorous, we need to denote these 2 things by different plus signs, but of course this is not inconvenient, and in every situation it is clear from the context what addition is being considered. That's why I will not comment on this further, and that's why we will just use the same plus sign to denote both of these operations. And the same thing can be mentioned about the property number 7, because here we also have 2 different multiplications. So here we multiply the elements of the field. In the right-hand side we multiply the elements of the field. So here lambda is multiplied by mu. Both of them are elements of the field f, and we multiply the first of them by the second, and so we get an element from the field. And in the left-hand side of this relation, we multiply a scalar, I mean the element of the field, by a vector, by the element of the vector space. And so this is the dot that is defined here. So we have 2 different multiplications in the property number 7, but exactly as in the previous case, it is more or less clear which multiplication is being considered in what situation. That's why we will not introduce different notation in order to somehow to distinguish between these 2 operations. Okay, so this is the definition, and let us make maybe a few more remarks, or maybe not remarks. I just will add this into this definition, that elements of V are called vectors. Then this 0 is called the 0 vector. We will later prove that it is unique. And the operations plus and dot are called the addition and the multiplication by scalars respectively. So this is the definition, and before we give some examples, let us discuss some simplest properties of all vector spaces. So 1.2 simplest properties. So now I'm going to show that some properties typical for the coordinate space Rn follow from this definition, so follow from this abstract definition. So proposition let V plus dot be a vector space over F, where F is the field, and so I will denote, just in order to shorten the notation, I will just write it like this. So let this triple be a vector space over F. Then the following properties are satisfied. So the first property, a zero vector, I will write it like this, is unique. So it follows from the definition that it is unique. An additive inverse minus V is unique for every V from V. Then 0 multiplied by V equals the zero vector for every V from V, and so this would be A, and B, lambda multiplied by the zero vector is also the zero vector for every lambda from the field. So this is the third property. Then the fourth property, that minus 1 multiplied by V equals minus V for every V from V capital. So here minus 1 is the additive inverse in the field. And then the last property, if lambda multiplied by V equals the zero vector, then either lambda equals 0 or V equals the zero vector. So these are the 5 properties that we're going to prove. So something very similar to the first 2 properties we have already proved when we were talking about groups, fields, and all that. So I'll be very brief. Proof so if 0, 1 and 0, 2 are two zero vectors, then 0, 1 equals 0, 1 plus 0, 2. So this follows from the fact that 0, 2 is the zero vector, and so this is the consequence of the property number 3, and by the same argument this equals 0, 2, just because 0, 1 is the trivial element. So this proves the first property. Then the second property, so let let U and W be inverse elements for the vector V from the space V capital. Then U equals U plus the zero vector. So this follows from the property 3. Then the zero vector can be represented as the zero vector can be represented as V plus W, just because they are inverse to each other. So U plus V plus W. So this follows from the property number 4, because these elements are assumed to be inverse to each other. And then we can use the associativity property, so I can rewrite it as U plus V plus W. So this is the property number 2. And then these elements are also assumed to be inverse to each other. That's why we get 0 plus V. So this is the consequence of the property number 4. And then once again we use the property number 3 and we get W here, just because 0 is the trivial element. Sorry, not 4, but it should be 3 here. So here I'm going to show how different properties, how different parts of this definition can be used in order to prove the properties from this proposition. So now we proved the first two properties, and so now let us move on to the third property. So 3a. So we're going to consider the element 0 multiplied by V. So 0 multiplied by V equals 0 plus 0 multiplied by V. So it follows from the fact that 0 is the additive inverse in the field. And then I'm going to use the distributivity property. So this is the property number 6. So it follows that this thing can be rewritten as 0 multiplied by V plus 0 multiplied by V. So this is the property, this is the consequence of the property number 6. Okay, so 0 multiplied by V equals 0 multiplied by V plus another 0 multiplied by V. And according to the property number 4, so it follows from 4 that there exists minus 0 multiplied by V such that 0 multiplied by V plus minus 0 multiplied by V equals the zero vector, right? And so I'm going to add this element to both sides of this relation. So what are we going to get? We're going to get 0 equals 0 multiplied by v plus minus 0 multiplied by v. So it follows from the property number 4. And so here we have 0 multiplied by v plus, 0 multiplied by v plus another 0 multiplied by v plus minus 0 multiplied by v. And then I'm going to use the associativity property, which is number 2. So I will represent it as 0 multiplied by v plus 0 multiplied by v plus minus 0 multiplied by v. So this is what we are going to get, and this is 0, so 0 multiplied by v plus 0. So it follows from the property number 4, and then here we get the 0 vector, so we have the sum of some vector with the 0 vector, so we get this vector, and we come to the conclusion that 0 multiplied by v equals 0. So this is exactly what we intended to get. So this is the first part of the third property, and now let us consider the second part of the third property. So this would be the property b. So lambda multiplied by the 0 vector. So lambda multiplied by the 0 vector can be represented like this. So lambda multiplied by 0 multiplied by the 0 vector. So we know that the 0 vector multiplied by any scalar gives the 0 vector. We have already proved this. So this follows from the property A, that the 0 vector can be represented like this. Okay, and now we can use the property number 7, just because here we have this kind of a product, so I can rewrite this product as lambda multiplied by 0, where this dot is the multiplication in the field, multiplied by the 0 vector. And when we multiply something by 0 in the field, we get 0, so we have 0 multiplied by the 0 vector, and it follows from the previous property, from the property A, that we get 0 here. We get the 0 vector. So this thing follows from the property number 7, right? And so I'm wrong, because not this implication follows from the property A, but this one. So the previous follows from the properties of a field. Okay, so this proves the fact that when we multiply the 0 vector by any constant, we get the 0 vector. And so this completes the proof of the third property. Then the fourth property. So we need to show that the vector minus 1 multiplied by v is the additive inverse to v. We know that it is unique, that's why it is enough to show that their sum is the 0 vector. So consider minus 1 multiplied by v plus v. And we need to show that this is the 0 vector. So I'm going to use the property number 8 in order to represent v as 1 plus v. So it follows from the property number 8 that any vector can be represented as 1 multiplied by itself. So I'm going to use this property, and then I'm going to use the distributivity property number 6. And we are going to rewrite this as minus 1 plus 1 multiplied by v. Okay, and so this is the addition in the field, so we get 0 multiplied by v, And we already know that when we multiply the 0 from the field by any vector, we get the 0 vector. So it follows from the property 3a. So I will just denote it by a, just because there are no other a's here. Okay, so this proves that this vector is the inverse for v. And finally, the last property. So here we need to prove that if lambda multiplied by v is the 0 vector, then either lambda is 0 or v is the 0 vector. So assume lambda multiplied by v equals the 0 vector, and lambda is not 0 in the field. Then, according to the definition of the field, there exists the multiplicative inverse lambda to the minus 1, such that lambda to the minus 1 multiplied by lambda gives 1, gives the multiplicative identity in the field. I'm going to consider the 0 vector, and the 0 vector can be represented as lambda to the minus 1 by the 0 vector. So it follows from the property B. And then, according to our assumption, lambda multiplied by v is the 0 vector. So we can write it like lambda to the minus 1 multiplied by lambda v. And then we are going to use the property number 7. So we get lambda minus 1 multiplied by lambda and then multiplied by v. So this is the multiplication in the field, so we get 1 multiplied by v, and according to the property number 8, 1 multiplied by v is just v. So from this assumption and from the assumption that lambda is non-zero, we come to the conclusion that v is the 0 vector. So this proves the proposition. Okay, and so I will just make a remark that we will write u minus v instead of u plus minus v. So when the vector, the additive inverse to the vector v is added to u, we will just write u minus v. So this is something common for other situations. Okay, so these properties follow from the definition of a vector space, and my aim was to show how to use these axioms, how to prove some results using the formal arguments based on the axioms or based on the properties from the definition of a vector space. Okay, and now we will consider several classes of examples. So 1.3 important classes. Classes of examples. Okay, so the first example is just geometrical vectors. So or just vectors joining points on a plane or in 3D. So geometrical vectors. So we can add geometrical vectors. So consider one vector u and then another vector v, right? So we can add them. So this is u plus v, and for any given number we can multiply a vector by this number. So if this is vector v, then we can just consider the vector that is collinear to v, and such that the magnitude of this vector is lambda times magnitude of v. And so this is the way how we add vectors and multiply them by real numbers. And of course this gives us an example of a vector field, of a vector space. So obviously all the properties are satisfied for geometrical vectors. So this, so the set of geometrical vectors on a plane, or the set of geometrical vectors in three-dimensional space, forms a vector space over the field of real numbers. The second example is just the maybe the most important example: coordinate spaces. R to the n, maybe complex coordinate space C to the n, or F to the n, where F is a field. So these are just these are n tuples of elements from F, and we can obviously add these elements by setting the sum of the two tuples to be equal to the tuple that consists of the sums of elements in each row. So the addition here is component-wise, and in the same way we multiply a tuple of coordinates from the field by some element from the field. So this is just lambda multiplied by x1, etc., lambda multiplied by xn. Obviously all the properties are satisfied just because they follow from the properties of a field. So in a field elements are commutative, so multiplication is commutative and addition is commutative, and that's why all the properties are satisfied, obviously. So this is the structure that is inherited in some sense by any vector space, and we will discuss this further. Then the third class of examples would be spaces of polynomials. So I will introduce the following notation. So let R of x be the space, or maybe the set of all polynomials with real coefficients. And so we can add two polynomials so p plus q of x by the definition is just p of x plus q of x, and we will also get a polynomial. And we can multiply polynomials by scalars. So lambda multiplied by p, what is the polynomial lambda multiplied by p? So this is such a polynomial that its value at the point x is lambda multiplied by p of x, right? So all the coefficients of these polynomials, of this polynomial, are multiplied by the same lambda. And so obviously all properties are satisfied. Just because they follow from the properties of real numbers. All properties, I mean all properties in the definition of a vector space. So then consider the set of polynomials with degree not greater than n. So I will denote it like this. So this is the set of p from R of x such that the degree of p is less or equal than n. So when we add two such polynomials, we also get a polynomial of degree not greater than n. When I multiply such a polynomial by some constant time, I also get a polynomial of degree not greater than n. And so obviously all the properties are satisfied just because they are satisfied in the larger set of all polynomials. And so in the same way, one may define the spaces of polynomials with coefficients from arbitrary field. Of course, they are also vector spaces over F. So this gives us another important class of examples. Then spaces of matrices. So consider matrices of the size n by m with entries from a field F. So I will denote this space by mat mn of F. So we considered matrices with real entries, but in the same way we can consider matrices with entries from some arbitrary field. And so we can add matrices. We can multiply them by scalars from F, and all properties from the definition are satisfied because they are satisfied for elements in the field F. And so when we add matrices, we just add them component-wise, and that's why if some property is satisfied for all elements from the field, then this property is satisfied just for for the same properties is satisfied for the matrices. So I will not go into the details because it's more or less obvious, but nevertheless, we have another example, another important example of a vector space. And here I would like to stress that these examples show that we somehow that this definition somehow allows us to extend the concept of a vector space from the modeling example that we discussed here, from the example from example number 2, to more general situations. So in case of example number 3, the vectors in these vector space are polynomials. So we consider polynomials as vectors. In example number 4, we consider matrices as vectors. So the element of this vector space is a matrix, and we work with matrices as with vectors. So since our definition is very general, we can apply this definition to any to different situations, and in particular we can apply our definition to these kind of situations. So here we work with the elements of some other spaces as vectors, and since since the standard properties are satisfied, we can apply this definition to this object, and then we will study the properties of this general algebraic structure, and that's why we will get consequences for any vector spaces, like space of matrices or space of polynomials and all that. Okay, example number 5, or maybe better to say class of examples, functional spaces. So consider the space of all functions continuous in the interval from A to B. So this is the huge set. This is a huge set of functions, and we will denote it by C of AB. This is the standard notation. C stands for continuous, and so we can add two functions. So if f and g are both continuous, then f plus g also is a continuous function in this interval, and so f plus g is defined pointwise. So the value of the function f plus g at the point x is equal to the sum of f of x and g of x. So in the same way, we can multiply a continuous function by some scalar. So if we take the sum of the two functions from C of AB, then the sum belongs to the same space, and for any lambda, for any real lambda, we also have that lambda multiplied by f is also a continuous function, right? So we have the two operations, and all the properties from the definition of the vector space are also satisfied, just because the operations are defined pointwise. So C of AB is a vector space over the set of over the field of real numbers. And in the same way, one may consider the space I of AB of Riemann integrable functions in the interval from AB, or all the space of smooth functions, and so there are many different examples. And so this is not just one example, but the huge class of different examples, functional spaces. So the next class, maybe the last for today, are spaces of sequences. So the set of all convergent sequences of real numbers form a vector space over the field of real numbers, obviously, just because we can add sequences, we can multiply them by numbers, and if you take two convergent sequences, then their sum is also a convergent sequence, and the same works for the multiplication of a convergent sequence by a number. So, and all the properties are satisfied by the same reason. So the operations are defined component-wise, and that's why all the properties are satisfied. Or similarly, one may consider the space of all bounded sequences, both form a vector space over R, since the operations with sequences are defined component-wise, and therefore everything is satisfied for the elements of the set of real numbers, and that's why the corresponding properties are satisfied for the sequences themselves. So these are the most important classes of examples of vector spaces, so we will consider them further, and I would like to stress that this definition allows us to extend the things that we do with the coordinate space to other vector spaces of arbitrary nature, like spaces of functions, spaces of matrices, or polynomials, or whatever. Okay, the next section, 1.4, vector subspaces. Sorry, I usually write this in green. So we will start with the definition. Let V be a vector space or maybe I'll better say that not V, but the triple, because I will need to specify the operations in this vector field, in this vector space. So let V plus and dot be a vector space over F, and let U be a non-empty subset in V. Then U is called a subspace, or a vector subspace, a linear subspace in V, if the following two properties are satisfied. U plus V belongs to U for any U V from U, and the second property states that lambda multiplied by U belongs to U for any U from U capital and for every lambda from the field. So in this case, the subset is called as a subspace in V. So I would like to make a remark that any subspace U in the vector space V plus dot is also a vector space with respect to the same operations plus and dot. So why? If all the properties from the definition are satisfied for all vectors from V, then in particular they are satisfied for those vectors that belong to the subset U. So that's why all the properties are satisfied, but the only thing that we need to check is that when we apply these operations to the elements of the set U, we do not get outside this set. So that's why we require that U plus V is from U and lambda multiplied by U is also from U. So if we consider the set that satisfies these two properties, we always get another vector space with respect to the same operations that were defined in the ambient vector space. So this is more or less typical for any algebraic structure. And so let us consider a couple of examples. So let V be the space of all polynomials with, or maybe I will just consider polynomials with real coefficients. So let V be the space of polynomials and let U be the set of all polynomials in this space such that P of 1 is 0. So obviously it forms a subspace in V, just because if we add two polynomials having a root in having a root at 1, we will also get a polynomial with a root at 1. And if we multiply such a polynomial by any constant, we will also get a polynomial that has a root at 1. So we obviously get a subspace. So this was the first example here, and then maybe 2 more examples. So the second example, let V be the space of all n by m matrices with entries from the field of real numbers, and let U, or maybe I'll better consider not the space of n by m matrices, but the space of square n by n matrices. And let U be the set of all symmetric matrices. So these are the matrices such that the transpose equals A. So obviously U is a subspace in V, just because the sum of 2 symmetric matrices is also a symmetric matrix, and the product of a symmetric matrix by any scalar is also a symmetric matrix. And so the same works for matrices with entries from other fields. And finally, the set of solutions of a homogeneous system A multiplied by x equals 0, where A is an n by m matrix with entries from some field. So the set of solutions is a subspace in the coordinate space f to the m. So, as we discussed earlier, all the algebraic properties are inherited by any field, and that's why everything that we discussed concerning the solution spaces of linear systems can be also stated for systems with coefficients from arbitrary field. That's why we also get an example of a subspace, of a linear subspace in the coordinate space, but in this case we consider coordinate space f to the n instead of r to the n. Okay, so the next subsection 1.5, linear dependence. So I will be very brief, just because here everything is exactly in the same way as in the coordinate space. So let V be a vector space over F, where F is the field, and so in the same way a linear combination of vectors from V is a vector of the form alpha 1 V1 plus etc. plus alpha k times Vk, where alpha, where alphas are the coefficients in the field. And so exactly as it was in the case of a coordinate space, we call such thing a linear combination. So in this case, exactly as in the coordinate space, we can multiply vectors by constants. That's why we can consider linear combinations of vectors. So a linear combination alpha 1 multiplied by v1 plus etc. plus alpha k multiplied by vk is called non-trivial if at least one of the coefficients is not zero. So otherwise, such a linear combination is called trivial. This is also exactly as it was in the case of a coordinate space. And so a family of vectors v1, etc., vk from v is called linearly independent, or linearly, better to say linearly dependent, if there exists a non-trivial linear combination of these vectors that is equal to the zero vector. So sometimes I write this zero vector with the arrow, but of course I will not put the arrow in all the cases just because it is more or less obvious. So the definition of linear dependence of the family of vectors is exactly the same as in the coordinate space, and if the situation, if a family of vectors is not linearly dependent, then it is called linearly independent. So otherwise, linearly independent. So I'm very brief just because here we repeat all the definitions that we had before. And so now let me consider some example which will be important in our further considerations. So let V be the space of polynomials with coefficients from some field. Then any system of polynomials of different degrees is linearly independent. Indeed, consider a family of polynomials P1, etc., Pn, and having different degrees. And assume they are linearly dependent. So there exists a non-trivial linear combination equal to 0. So this is the zero polynomial. This means that this polynomial is identical 0. So the values of this function are zeros at every point. And so they are linearly independent. And so at least one of the coefficients is non-zero, and so let consider only non-zero coefficients in this linear combination, and let k be the number of the polynomial let k be the number of the polynomial pk with the highest degree, such that alpha k is non-zero. So since all these polynomials have different degrees, then there exists the polynomial with the highest degree, and so consider all the polynomials such that the coefficients are non-zero, and among them choose the polynomial p sub k with the highest degree, right? So its coefficient is non-zero. Let pk have the form, so a sub d multiplied by x to the d plus a sub d minus 1 multiplied by x to the d minus 1 plus etc. So this is the highest degree. Then the whole linear combination alpha 1 p1 plus etc. plus alpha k pk is a polynomial of degree d, just because among all the polynomials with non-zero coefficients, p sub k is the polynomial with the highest degree. That's why the degree of the whole expression would be exactly d. So the leading coefficient of this polynomial is alpha k multiplied by the leading coefficient of p, which is a sub d. And since alpha sub 1 times p1 plus etc. plus alpha sub n times pn, it should be n here as well, is 0, all the coefficients of this polynomial are zeros, and in particular the leading coefficient is also 0. Alpha k multiplied by a sub d is 0. But we come to a contradiction because both of these coefficients are non-zero. So we come to a contradiction. Note that here we use the properties of a field. So when we considered fields, we discussed that in any field there could be no zero divisors. And we use this property here, just because in a ring this would have not been true. Just because in a ring there could be zero divisors, but in a field there are no zero divisors. That's why this relation implies that both of these elements are zeros, and that's why we come to a contradiction. That's why any family of polynomials with different degrees is linearly independent. So this is important. Okay. We discussed this example, and besides this we need just to say a few more words about the things that we have already discussed, but nevertheless I'll just say this very briefly. So another kind of definition. So let V be a vector space over F. So let V1, etc., Vk be vectors from V, then the span of this family is defined as the set of all vectors from V such that V has the form alpha 1 times V1 plus etc. plus alpha sub k times V sub k. So this is the space of all linear combinations of these vectors. So exactly as in the case of the coordinate space, the set is called the span of vectors. And so I will be just very brief because we have already discussed all these things in the coordinate space Rn, and everything is similar here. So we had a theorem that describes the relation between a linear dependence or linear independence of a system of vectors and its subsystem. So, for example, if some family of vectors is linearly dependent, and we add some more vectors, then it will be still linearly dependent. And so, or maybe if some family of vectors is linearly independent, but when we add some more, but when we add a vector to this family and the whole system becomes linearly dependent, this means that the vector that we add is a linear combination of the vectors that we had. So we had a statement with a number of properties like this. So I will not reformulate all of them just because they are formulated exactly in the same way in the general situation as in the coordinate space, and so they are all satisfied. We will just use these properties without reformulating them once more. And so 1.6, basis and dimension. So we have also discussed the notion of a basis in a subspace in the coordinate space and the dimension of a subspace. So these notions also can be extended to the case of arbitrary vector space. And so let us just do this very briefly, because there is nothing new in fact. So let V be a vector space over the field F. Then a linearly independent family of vectors v1, etc. Vn is called a basis in V if the span of these vectors coincides with the whole space. So if this space is just the set of all linear combinations of these vectors, and these vectors are linearly dependent. And so another definition: a vector space V is called finite dimensional if there exists a finite basis. We will not consider infinite basis, so I will just, and here in the definition of the basis we assume that it is finite, but I just want to stress that the basis should be finite. It's called finite dimensional if there exists a finite basis. And so let us just note that the space of all polynomials is not finite dimensional. Why? So assume there exists a finite basis that consists of polynomials P1, etc., Pn. So since this family of polynomials is finite, there exists a polynomial with the maximal degree. I mean the maximal degree among these polynomials. So let D be this maximal degree. This means that any linear combination of these polynomials has the degree not greater than D. That's why any polynomial Q such that the degree of Q is greater than D cannot be expressed as a linear combination of P1, etc., Pn. That's why they do not form a basis. So if we assume that that there exists a finite basis in this space, we come to a contradiction that these vectors do not form a basis. Another example. A family of polynomials one x, x squared, etc., x to the n forms a basis in the space of polynomials of degree not greater than n. So we already know that they are independent. Independent as polynomials of different degrees, so we have already proved this. And for every polynomial p from this space, we have p equals a sub n multiplied by x to the n plus a sub n minus 1 multiplied by x to the n minus 1 plus etc. plus a1 multiplied by x plus a naught. So this is a linear combination of polynomials xn, x to the n minus 1, etc., x and 1. So we can represent every polynomial from this space as a linear combination of these polynomials. That's why they form a basis in this space. And in the same way, a family of matrices E sub ij from the space of matrices with n rows and m columns, and entries from some field form a basis in this space where E sub ij is the matrix such that it has just one non-zero element at the ith jth position. So this is 1. So this is the only non-zero element in this matrix. So all other elements are zeros. So these matrices form a basis. Just because they are obviously linearly independent, I will not comment on this just because this is quite similar to the things that we discussed before. So these matrices are linearly independent. And for every matrix A from the space of matrices with n rows and m columns, we have A equals the sum where I ranges from 1 to n and j ranges from 1 to m of A sub ij multiplied by E sub ij. So we can represent any matrix as a linear combination of elementary matrices of this kind, and the coefficients are exactly the elements of this matrix, and that's why these matrices form a basis in the space of all matrices with n rows and m columns in our vector space. Okay, and so these are two examples that are in some sense new, because here we consider a basis in a space that is not the coordinate space. And now I will formulate a lemma that we have actually discussed before, but it is quite similar to the case of a coordinate space. So let V be a vector space over F, and let V1, etc., Vn be a basis in V. Assume the system W1, etc., Ws is linearly independent. Then S is less or equal than n. So this lemma is proved exactly in the same way as such lemma for the coordinate space Rn that we proved a few lectures before, so I will not repeat the proof. And it follows from this lemma that the number of vectors in any basis in a finite dimensional space is the same. So it is just a corollary of this lemma. So let V be a finite dimensional vector space over F, then the number of vectors in all bases in V is the same. So it immediately follows from this lemma, and we will call this number the dimension of a vector space. So the number of vectors in a basis of a finite dimensional vector space is called the dimension of this vector space. So this notion is also not new, because when we discussed subspaces in the coordinate space Rn, we introduced the notion of the dimension of a vector subspace. But here we consider the more general situation, and if our vector space is finite dimensional, then there exists a finite basis, and it follows from this lemma that the number of vectors in every basis in this space is the same, and that's why we can call this number the dimension of a vector space. And so I will finish with considering a couple of examples. So the first example is that the dimension of the space of polynomials with coefficients from arbitrary field is n plus 1, just because we have n plus 1 vectors in a basis. So we have vectors starting from 1 and ending at x to the n. So we have n plus 1 vectors in this basis. And another example, so the dimension of the space of all matrices with n rows and m columns and with elements in some field is n multiplied by m, just because we have n multiplied by m vectors in the basis that we just introduced in these fields. So we have n by m matrices of this kind. So in this case, in this case, we have just one at some position, and there are n by m different positions where we can put a 1 there. And so this gives us two examples of finite dimensional spaces. And maybe one more definition that is also actually not new. So let V be a vector space over F, then the rank of a family of vectors v1, etc., vk is the dimension of the span of this family of vectors. This is also the thing that we have discussed earlier in the situation of the coordinate space Rn. So in the general case, we also use this notion. So that's it for today, and at the next lecture we are going to continue to discuss vector spaces and some special characteristics of these vector spaces, some special properties of vector spaces that will be new. So today's lecture was partially a review of what we discussed earlier, but in a more general situation. But at the next lecture we will consider things that will be essentially new. So that's it for today.